All right, kiddos, welcome back to Miss Schwartz's amazing video series over symmetry. Today we are really just talking about some symmetry. So it's a pretty short lesson. So our goal today is to really determine what type or types of symmetry each figure has, and we will be working with both two-dimensional figures and three-dimensional figures, and sketch the possible line or lines of symmetry or determine the angle of rotation. If you need additional information, this can be found in your book on page 167. So here we go. You should have some typed notes to go along with this so you do not have to draw any of the pictures. All right, so example one. If we look at the three shapes, which really should be labeled A, B, and C, we are going to determine if they have lines of symmetry, rotational symmetry, or both. And if they have a line of symmetry, then we're going to sketch the line of symmetry. And if they have rotational symmetry, we are going to determine the degree of rotational symmetry. So figure one is a heart. And if I look at the heart, I think most of us can realize that there is a line of symmetry that goes right down the center, where the left side of the heart and the right side of the heart look identical. However, if I start rotating the heart, so if I rotate that heart 90 degrees, that heart would look something like this. And because it does not map exactly onto itself, then it does not have rotational symmetry. Okay, same thing if I rotated 180 degrees, a really bad example drawing would look like that. And 270 degrees, we would have a heart that goes to the right, and so none of those would map onto itself. So a heart really has one line of symmetry, and it cuts it in half vertically. So looking at the next figure, it's kind of like a multiplication sign. So if I think about what's happening about lines of symmetry, if I look at this figure and I draw a line right down the center, I do have a vertical line of symmetry. I could also cut it horizontally, so I have a horizontal line of symmetry. And even on this one, I could cut it in half here, and this top side here would map onto this bottom side here. So I actually have a 45-degree line of symmetry. And because I could go with that 45-degree line of symmetry, I could also switch and I have a line of symmetry here. So in this particular shape, you have 4 different lines of symmetry that would cut the figure in exactly half, such that side 1 would reflect and map onto side 2. This figure also has some rotational symmetry. So if I started with this point right here and I rotated it, it would end up 90 degrees later right here, and that figure would map onto itself, and I could do that 2 additional times. So if I think about the fact I can turn that 4 times and it maps onto itself, if you take 360 divided by 4, you get 90 degrees. So this has 90-degree rotational symmetry. If you rotate it 90 degrees, it will map onto itself. An additional 90 degrees, maps it onto itself, 90 degrees and 90 degrees until you get back to where you started. All right, the double-sided arrow. So looking at the double-sided arrow, I want you to hit pause and take a minute and see if you can determine what type of symmetry this figure has. All right, welcome back. So if I look at this figure, I have this amazing arrow right here. And if I take that arrow and I rotate it 180 degrees, so if I think about rotating it 180 degrees, this tip right here, if I rotate it 180 degrees, ends up on this tip right here, and the arrow will be a perfect match. So you could think of it like this: 360 divided by 2 is 180. So it has 180-degree rotational symmetry. And I can also think that if I draw a line right here, that the left half would map onto the right half, it would reflect over that line. And again, if I drew a vertical line through the points of the arrows, the top half would reflect and map exactly onto the bottom half. All right, so now let's take some figures. This figure is a regular octagon, and the word regular is important because it means that the sides are congruent and all 8 of the angles are also congruent. So if I really think about rotational symmetry first, I could take this point, and if I turn it, it would map onto this point, this point, this point, this point, this point, this point, and this point. So it's an octagon, so there were 8 of those points, and mainly because it's regular, like this only works because this is regular. There are other non-regular octagons that could have some sort of symmetry, but where you turn it 8 different times only works if you have a regular figure. So when I do my division, I get 45 degrees. So this has 45-degree rotational symmetry. And if I start drawing my lines of symmetry, if I think about what happens, I can take this line and I can cut the figure in half this way. And I can actually do that 4 different times, because I could come along here and draw this one, come along here and draw this one, and come along in here and draw this one. So if I'm thinking lines of symmetry, I just found 4 of them. So right now I have 4 lines of symmetry. 1, 2, 3, 4. So now I got to think if there's any other lines of symmetry. So if I look at this octagon, if I connect these opposite vertices, that also cuts the figure in half. And so when I come over here and I start drawing these, there are 4 of those. So that gives me 1, 2, 3, 4 additional lines of symmetry, which in the end is going to give me a grand total of 8 lines of symmetry. All right, moving forward to example 3, let's think about some 3-dimensional figures. So if I think about a roll of toilet paper, if I just take a roll of toilet paper and cut it in half, thing is, let's just assume that this little flap right here is taped down and not hanging down. So let's assume it's like a brand new roll of toilet paper. I can cut that in half infinitely many times, and the left half is always going to look like the right half. So in a sense, this is going to have infinite reflectional symmetry. And if you take right here and you come in and we draw a line that kind of goes right through the center of this roll of toilet paper, and they'll come out this side right here. You could take and you could spin that toilet paper around all you wanted to, and it's still going to look like the exact same roll of toilet paper. So it also has infinite rotational symmetry. If I think about a stapler, I could take this stapler and I could hold it in the air and I could turn it and I can rotate it. It's never going to map onto itself. So when I look at that stapler, like if you turn it 180 degrees, the staple part up here in the front would end up back here, and those two sides don't look alike. The side up here on the top does not look like the bottom. So for a stapler, there is no rotational symmetry. So there is no rotational symmetry for a stapler. If you want to take this, you could get a stapler out of the classroom and you could hold it and you could look at it yourself. However, you could start at the top and you could draw a line that kind of cut your stapler right here. So if you kind of cut the stapler in half right along here and right along the back and then up the front, the left side would look like the right side, or the front side would look like the back side, depending on how you're looking at it. So there actually is going to be 1 line of reflection. So all I can do is really encourage you, when you have objects and you're doing your homework, is to really think outside the box and look at the shapes and the figures from some multiple perspectives, because some of them have some angles of rotation and lines of rotation that won't stand out to you immediately, but if you really kind of think and dive into your figure, you will be able to figure them out. All right, short lesson today. You have a very short assignment over this lesson, and I look forward to seeing you when you come back to class. Have a wonderful evening, and I will talk with you tomorrow. Bye-bye.